In this review video, I'm going to go over some very high-level nuts and bolts of what you probably already remember from fluid mechanics. The reason I'm doing this is because the whole point of CFD is to essentially solve the same equations that we're used to solving in fluid mechanics numerically, because we can't solve them on pencil and paper. So the fact of the matter is, in order to solve the equations that is describe fluid mechanics, can really only be done on pencil and paper or analytically for a really small set of very simplified situations. Oftentimes we're making really sweeping assumptions to do that, like assuming the flow is uniform, it's laminar, we have fully developed flow, things that are very simplifying that really don't reflect what we oftentimes are interested to learn about real life. So the first step in doing that endeavor is to understand, well, what are the equations that we're solving? And the answer is that we're solving conservation equations. So we're conserving mass, momentum, and energy. And these are the three big conservations that are going to come up. If you look at more complicated situations like fluid flows that are reacting, for example, you may also have to conserve species. But in general, anytime that you're conserving a quantity, it's going to take on the following sort of general form. And that form, for some variable or some quantity that we care about, phi, where phi could be a scalar, it could be a vector, or a tensor. It doesn't matter. This general form will always hold. Okay, so the first term that we have is we want to know how this quantity is changing in time, right? So this is what we'll call our rate of change of phi. All right, since we're writing it as positive, this is the rate that phi is increasing using this convection. The next term that we have is our velocity vector dotted with the gradient of phi. And this gives us the transport of phi through the mechanism of convection. So how is phi changing as the fluid is carrying it along by means of it moving? All right, so this is transport of phi by convection. All right, on the right-hand side, we are going to have a term that has a coefficient d, and then the Laplacian of phi. And so this is how is phi changing due to diffusion. All right, and here d is our diffusivity, or diffusion coefficient. And then finally, we're going to have some source term of phi. So this will be our source or sink of phi. All right, so as it's written here, this would be a source. If it becomes negative, it would be a sink. Okay, so this is our general form, and you're going to see as I write out the conservation equations of mass, momentum, and energy, they all take on this exact same form. All right, so let's start with mass. This one's a little one, so I'm just going to include it right down here. So if we have mass, we know that our change in the density over time is equal to the divergence of rho times u. All right, so we know that matter cannot be created or destroyed, and so we just have the change in matter in the domain is essentially equal to the amount of matter being convected into the domain, and then any compressibility effects. So since we have rho and u still in this divergence term, we could have matter being squished in. as well. All right. The next one that we have is conservation of momentum. And the conservation of momentum is the change in momentum plus the divergence of rho u cross u is equal to any body forces that we have on our fluid, and then any forces due to stress. So these are surface forces, these are body forces, and then this is our convection term. Convection. And then, of course, this is our rate of change. All right. Okay, and then let's see. And then last but not least, we have conservation of energy, where in the energy equation specifically and the mass equation, we will have additional terms appearing here if we're having a gas that has multiple components in it and those components happen to be reacting with each other. So that's a much more complicated situation. I'm not going to write those terms here, but they could arise, just so you're aware. Okay, so here we've got our time derivative of the total energy, so how our total energy is changing over time, plus our convective transport of energy, and that's equal to our diffusion of our heat plus a heat source plus our work of pressure and viscous heating. So that's going to look like the divergence of our stress dotted with the velocity. And then plus density times any body forces dotted with the velocity. So this is work of body forces this is work of pressure and viscous heating. So viscosity is kind of like a frictional effect. So that's what we mean by viscous heating. This is our heat source. This is diffusion of heat. And this is our convective transport of energy. And then obviously this is our time rate of change of the energy in the domain. And so these are really the building blocks of what CFD is going to be built on. And what we want to learn to do is how do we treat these equations numerically and essentially zoom in on a teeny tiny little control volume and approximate what's happening over the control volume as linear, for example, and then just do that millions of times over a bunch of little tiny control volumes, all working together. And so that's what we're going to do next time.